Okay, let's have a look at torque, the next topic. So look at these things here. We talked about this before, but basically if you want to get a bigger turning force here, which is what torque is, it's a turning force. Or it's a turning effect, I guess, caused by a force being put on an object that can rotate. If you want to get a larger turning effect, you need to apply more force. So the actual torque that you get will actually be proportional to the force that you get. So if you plot a graph of that and do a study of force exerted on a turning object versus the torque that you actually receive, you will get a straight line through the origin, and therefore you can actually conclude that the torque is proportional to the force. But if you're sort of thinking of a doorway there and you've got a handle there and it's free to turn around that axis here, then that rotation there will be better if you actually exert the force on the end there. So that position where the door knob is, the further the actual force is applied from the axis point there, or the fulcrum, this fulcrum here, the better you're going to get as a turning force there. So again, you can actually show that the torque is going to be proportional to the distance between the axis or the fulcrum and the actual place where the force is exerted. So you get your best combination of torque from those two. So it actually turns out to be force times by distance as a formula. So that's just something to keep in mind there. So the torque is equal to the force times by the distance. Okay. So a good example of this would be look at something like a seesaw here. So by the seesaw there, you actually got your fulcrum position there, and we're looking at two objects there. Say you've got a weight there of some sort, might be a person. Let's say they've got 50 kilograms as some sort of a weight there, and they're about 2 meters away. If you want to just sort of balance that out with say 10 kilograms, then we need to get the same sort of torque turning it this way, clockwise, versus the amount on the opposite side that's anti-clockwise, so that the seesaw is balanced. So if you look on the left-hand side here, the torque is actually force times by distance. So you'll be looking at 50 times by 2, which is 100, and this is in kilograms and meters, so that's a different unit there. So 100 kilograms times by meters. On the other side, to get exactly the same balance, we need to achieve the same thing. So in this side here, we need to get the same force times distance to give you a number of 100. So how is that going to occur? You've got 10 as the force. What distance do you need to place it at? 10 times by 10 would have given you 100. So this needs to be placed 10 metres away to get the same. The other way of looking at this is to think about in terms of, here we've got 1/5 of the actual mass now. To get the same torque, if we're going down to 1/5 of the force there, we would need to actually sort of go for 5 times the actual distance. So 5 times by 2, 10 metres. So that you can also think of it that way in terms of just understanding it. Now obviously this is used in lots of levers and stuff, so I've got some levers here. So if you look at levers, the levers that are applied here, you've got 3 levers here that work on by transmitting torque. So in the case here, you've got a lever involved which has got a fulcrum in the middle. Then it's got an effort being applied at the handles here, there's some sort of an effort. And then the load would go there, that's the thing you're trying to sort of squeeze or put a force on. So that's one type of lever there. But all levers have actually got that same relationship. So if you thought of a crowbar there of some sort, you would get some sort of a fulcrum point which hardly moves. It's like the pivot point or the axis point in some cases. You'll have some sort of an effort being applied up here by the handle, and you'll have some sort of thing you're trying to lift. So it might be a rock, or you're trying to get the lip off a case or something like that. But this might be the rock in this case. And you can use your lever to tip it up. So the effort that's applied here will actually then, of course, transmit and lift a load up there. Okay? So it's effort, fulcrum, and load. There are actually 3 classes of levers. So the first class lever has the fulcrum in the middle. So that would be the fulcrum in the middle. The second class lever, second class, I should just move that over. Second class lever, we'll try that again. Second class lever, lost it. There it is. The second class lever here has something different in the middle. Because if you look at this, this is your pivot point here, so there's your fulcrum that hardly moves. You're going to squeeze here and exert an effort, and your load here is going to squeeze the nut there, crush the nut. So in this case, the second class lever, you're actually looking at a situation where the load is in the middle. That's what a second class lever is, as opposed to a first class. If you look at this third class one, the part that actually does not move here is this part of the pole that's actually fixed in position. So there's your fulcrum. Okay. You've got an effort being applied here by the hand that's holding it, and they're actually going to lift the fish up there at some stage. So there's your effort there. And at the end here, just there, pulled down by the line and the fish, you're going to have your load. So in that case, it goes fulcrum and then effort and then load. And so in the middle there this time, you've actually got the effort there. So the effort's in the middle. So be the effort in the middle there. So if I think of it, I kind of think of it as flea. The three classes there. The first class has the fulcrum in the middle, second class has the load in the middle, and the effort is the third class one, so it's actually flea. F-L-E, it's actually flea. And that's how you remember them. Other thing to think about here is you can get equal torques on both sides of that lever, but the idea would be to have your load as a short arm to make a really small distance will give you maximum force, lots and lots of force. If you have that nut the nut placed in further into there, closer to the fulcrum, you will get a bigger force there for the same torque. Okay. So just look at some examples of these levers here, where you've got the part that's say shows the fulcrum. There's your load there, which is being squeezed. There's your effort, and so on. You can do the same thing with the sort of the nut there being turned by the spanner. Where the nut is, there's your fulcrum there. You're getting the load exerted on this force part there where it's going to be moved around, and the effort depends on where you have your hand. So obviously the further out you have your handle on the handle, that force being applied there, this distance away, will give you a very good torque and actually turn the nut better. Okay? You do the same sort of thing with spades there, trying to dig dirt up out the ground. The fulcrum will be that part of the spade that's up against the ground, it doesn't move. That'll lift the load up, and your effort's going down there. Now that's got the fulcrum in the middle, so that would be a first class lever. Because don't forget the flea there. First class lever in the middle, second class lever in the middle would be a load, and the middle part for an effort for the third class lever. So a couple of animations you can actually do on those. If you use a crowbar here, which has got a fairly long, short effort up there, you try and lift that up, you need more leverage there. So you could either move the actual fulcrum closer to the load to actually get a bigger force at a closer distance here for the same torque, or you could actually reset this. Or you could reset it here and try doing a longer lever arm there. You can see that the arm's getting longer there as you pull that down. And that would be a nice long effort distance to apply the same sort of force. You should get a bit of lift there. And that knocks the crate over. Okay, crash. All right, thanks.